All right, we have now nearly completed the basics of thermodynamics. The next parts of the class will all be applications of this basic stuff. And so I want to add now a few more formal relationships that we haven't talked about, and we probably won't use very much this semester, but I think it's good for you guys to have seen that these relationships exist at least. There are an enormous number of formal relationships in thermodynamics. The thermodynamics has been developed for a very long time, and people have derived many rather beautiful, logically beautiful relationships. The first of these that we'll talk about are the so-called Euler relationships. I won't derive where they come from because it takes us a little bit too far afield and would take too much time. But they come from the properties that we talked about earlier, the extensive and intensive properties associated with energy and entropy and enthalpy and Gibbs free energy and Helmholtz free energy. So we'll just take these as given, but let me say one thing. First of all, if you look at this first one for energy, for example, it looks a lot like the first law. The first law is du equals dq plus dw, right? But that's equal to TdS minus PdV plus mu dN. And so you can see that that's the same as this relationship, except for these differentials that are in there. But those differentials really matter a lot. This relationship, this Euler relationship, is not the same thing as this first law relationship at all. And in fact, well, I could go on about that. Suffice it to say that the Euler relationships are true, and you can use them in any situation whatsoever, but they're not the same thing as the differential relationships that come from the first law. And we'll talk about those differential relationships down below. So for the first one, it says that the energy is a combination of essentially a heat-like term and a work-like term, and basically this is a relationship between energy and other important variables like temperature and entropy and pressure and volume and chemical potential, which we'll now start talking about quite a bit more, and mole numbers. This term at the end, the chemical potential times the mole numbers, is correct as written for a pure substance, for a system that has only one pure substance. If there's more than one chemical species present, then this single term should be replaced by a sum of terms that has one chemical potential for every species in the system. So, oops, that should be a 2. So mu1, n1, mu2, n2, mu3, n3, and so on for every chemical species. And that's true for all of these relationships down here. I've just put the one term in there, but if there are many more chemical species present, then there's a sum of terms that replaces that. Same thing now for entropy. There's an Euler relationship, the energy divided by temperature, pressure, volume over T, minus chemical potential times N divided by T. And now from this one, essentially this top one, we can find Euler relationships for enthalpy, Gibbs free energy, and Helmholtz free energy using the definitions that we wrote out earlier. So for enthalpy, the definition is energy plus PV. If I take this expression now for the energy and plug it in there, you can see that this PV is going to cancel with this minus PV, and you're going to just be left with TS plus mu N as the Euler relationship for the enthalpy. Likewise, for the Gibbs free energy, if I plug in the definition of enthalpy and then plug in the definition for energy, everything cancels except just the mu N term. And now let me go down a little bit. I say that it's important for later to notice that that means that the chemical potential is almost the same thing as the molar Gibbs free energy, right? The Gibbs free energy per mole of whatever it is for a pure substance. This is true, and you will see in the literature very often that people will almost equate chemical potential with molar Gibbs free energy. We'll do something very much like that before very long in here too. But they're not quite the same thing. This is only true, this relationship is only true if there's only one substance in the system, or if you're just talking about one pure substance within a more complicated system. So not quite the same thing, in fact. All right, then for the Helmholtz free energy, we can do the same thing. We can plug this definition for energy in here, then the TS's, this minus TS cancels with that TS, and you just get PV plus mu n. All right, those relationships are occasionally useful, and I don't think we'll make much use of them in this class, but it's good for you to know that they exist. You will see them out in the literature quite frequently, and so I think it's good that you know that they exist and a little bit about where they come from and what they mean. All right. Then we now have several different related quantities, and these last four, in fact, are related to the second law of thermodynamics, but they can be written in a differential form. So this is the differential, the total differential of the entropy. And just solving for ds in this expression gives us this differential expression for the entropy. There are several implications from these. I've called these versions of the first law. This really is the first law as we saw it originally. But now you can see that by rearranging this version of the first law, we can get this expression for entropy. And then by substituting in for du in this definition for dH, we can also get a sort of first law-like differential expression for enthalpy, the same thing for Helmholtz free energy, and the same thing for Gibbs free energy. And those differential expressions have two implications, two important implications. The first one is that by looking at what the differentials are in each expression, we can tell what are the so-called natural variables for each quantity. So we can think of energy as being a function of other variables. And what are those variables? Well, you can choose any variables at all in principle, but there are some that are more useful and fit more naturally with the properties of energy than others do, and those are called the natural variables. And looking at the first law, we can see what those natural variables are. They're going to be entropy, volume, and mole numbers, and here they are. Likewise, for entropy itself, I can pick off what the natural variables are by looking for the differentials, and those are energy, volume, and mole numbers. Now, after a little bit of algebra, I get this differential expression for enthalpy, and again, I can pick off the natural variables, and they're entropy, pressure, and mole numbers. Likewise, for the Helmholtz free energy, I can get a first law-like differential expression, and the natural variables are temperature and volume and mole numbers. And finally, for the Gibbs free energy, again, a differential expression with natural variables, temperature, pressure, and mole numbers. Notice that in these last two cases especially, the natural variables correspond to the conditions for which the Gibbs free energy is most useful, right? The Gibbs free energy is most useful when I have a constant temperature, constant pressure process, and where the mole numbers are fixed as well, right? Because the walls are impermeable. And there they are. Temperature and pressure are the two variables. So when you're working with Gibbs free energy for a constant temperature, constant pressure process, these two variables are going to be fixed by the baths. That's one of the reasons, or another way of seeing, that the Gibbs free energy is really a useful quantity when dealing with constant temperature, constant pressure processes. And in the same way, the natural variables for a constant temperature, constant volume process are T, V, and N. These two guys are held constant, and that's why the Helmholtz free energy is the natural quantity to use and make use of for a constant temperature, constant volume process. All right. The second thing that these differential expressions tell us or imply are a whole bunch of derivative relationships. Again, we won't make heavy use of these derivative relationships. You'll see them occasionally in the book. I don't think I'll derive anything in class using them because it takes us too far afield. But you will see them heavily used in the literature, and so it's important that you know at least that they are out there. And here's how they work. Let's look again just at the energy. Here's the first law. This is dq, this is dw, dq rev, and dw rev, for a reversible process, that is. And here's the same differential expression from calculus. So this is an experimental expression up here. This wasn't arrived at from calculus, it was arrived at by doing experiments. But this bottom expression does come from calculus, and you can see that by comparing the two, that these two quantities ought to be the same, right? They've got the same differential ds in front of them. So if both of these expressions are equal to each other, that means these two quantities have to be equal to each other. And likewise, these two guys have to be equal to each other, and so on. And that leads to a whole bunch of relationships between the partial derivatives of the energy and physical quantities like temperature and pressure and chemical potential. So the temperature is equal to the derivative of energy with respect to entropy, holding volume and mole numbers constant. It is important to realize that the derivative, the variable that you take the derivative with respect to, entropy in this case, and the variables you hold constant all have to line up. If I wrote the derivative with respect to entropy holding temperature and chemical potential constant, for example, that's not the same derivative. That's a perfectly fine derivative, but it isn't the same one as this one down here. You gotta, for this relationship to work, all three things have to be correct. Both the variable you're taking the derivative with respect to and the things you're holding constant. Likewise, the minus the pressure is the derivative of energy with respect to volume, holding entropy and mole numbers constant. And chemical potential is the derivative with respect to mole numbers, holding entropy and volume constant. All right. Now we can do that same thing and get a whole bunch more differential relationships by using all these first law-like relationships that we just talked about. And here they all are, and I won't go through them all. There's a whole bunch of them. It's basically a whole table or arsenal of relationships that allows you to derive all kinds of new relationships and expressions that are useful in thermodynamics. If you get deeply into a field where thermodynamics is important, you'll end up using all these relationships. They're really powerful, and there's another set of relationships called the Maxwell relations that I won't even write down because this is already abstract enough and complicated enough that I don't want to confuse people further, but I just want to point out two of them that we will use. One of them says that minus the entropy is equal to the derivative of the Gibbs free energy with respect to temperature, holding pressure and mole numbers constant. We'll use that when we're talking about the Clausius-Clapeyron relationships. And the other one is that the chemical potential is equal to the derivative of the Gibbs free energy with respect to mole numbers holding temperature and pressure constant. That's the relationship that's almost always used in order to define what we mean by chemical potential. And you can see that it's kind of related to the relationship we saw earlier, that chemical potential for a pure substance is equal to the molar Gibbs free energy. This is a derivative. It's not the same as this relationship, but it's clearly related somehow. But this relationship is true even for systems that have many variables, whereas this one's only true, many substances, many species, chemical species. This one's only true for pure substances. So it's sort of the generalization of the earlier relationship. All right, so now you've seen that these abstract and complicated differential relationships exist, and you won't be surprised if they pop up again in another class, especially if you go on to graduate school, but even if you go on to work in industry, in a lot of areas of industry and in medicine, many areas, thermodynamics is extremely important. And these kinds of relationships do occasionally pop up. So even in non-research settings, maybe even especially in non-research settings, but also especially in research settings. All right, that's one set of relationships. Now let's come to a different set of relationships, and these we will use extensively in this class. These relationships aren't so formal and aren't so abstract. They're much more concrete. They're actually necessary for almost, we've been using relationships like this all along. I just haven't identified them as sort of members of a class before, but now I'm grouping them all together and saying, let's call this group of relationships the standard equations of state. You need an equation of state, maybe more than one equation of state, pretty much every time you do a thermodynamic calculation. So what are the standard ones? Bear in mind that there are other ones. I'm not giving you all the possible equations of state because there's practically an infinite number of them. But this is the set that's probably sufficient for pretty much everything we're going to do in this class. So if you don't remember anything else from this lecture, remember this list of standard equations of state. They come in groups. There's ones that have to do with pressure and volume, there's ones that have to do with energy and temperature, and there's ones down here that have to do with mole numbers and chemical potential, and we'll go through them. So first, the pressure-volume ones. It depends on what kind of system or what kind of species you're talking about. There are gases, and for pressure-volume relationships, also liquids and solids, and you don't really need to know anything more than what state or what phase the system is in. If it's a gas, then the ideal gas law is an equation of state, and we've seen that we need the ideal gas law right and left in all the calculations we've done above. This equation of state isn't the best one ever, it's just the simplest one. There are much more accurate ones, and those work for non-ideal gases as well as for ideal gases. The van der Waals equation of state is one I think probably many of you have seen that. We won't talk about those things because they're really kind of a little bit of window dressing for this class. So let me just make you aware that there are better equations of state. But for our purposes, this is nice and simple. It's also universal. Notice that this equation of state doesn't depend on what kind of gas it is. It's the same equation of state for oxygen as for helium as for methane or anything else. And that's really nice. All the other better equations of state depend on which kind of gas you have, and you've got to look up special parameters for them and stuff like that. So the ideal gas law is really nice. And that, therefore, we'll use it in all the cases that we use here in this class. It's accurate enough for our purposes. Then for liquids and solids, the fact is that it's really hard to compress a liquid or a solid, as you can imagine, right? Imagine putting some water into let's say a steel cylinder and standing on a plunger. Will you compress the liquid? Geez, even 100 pounds of pressure is probably not enough to appreciably compress a liter of water. You got to really press hard. You got to really raise the pressure hard before you start appreciably compressing either a liquid or any solid. And so the approximation we're going to make is that liquids and solids are incompressible. That is an approximation. They really are compressible a little bit. It's just that they're not very compressible. And given that approximation, what we're going to do is just say that the molar volume, the volume of the system per mole of water, or per mole of steel, or per mole of, I don't know, silicon, is some constant value. You have to look up what that constant value is, right? It's the molar volume, or if you like, the density of the molar density of the substance. But once you know that value, it's a constant, and you can use that fact in all of your calculations. All right, that's the pressure-volume relationships. Now, moving on to the energy and temperature relationships. We've already seen these. I didn't identify them as equations of state before, but now we will. they relate the energy to the temperature. That's why I'm calling them energy-temperature relationships. And they're basically just the CV or CP relationships that we saw earlier. The CV is equal to the derivative of energy with respect to temperature holding volume constant, and CP is the derivative of enthalpy with respect to temperature holding pressure constant. And so you can see that that leads naturally to these approximate relationships. And for monatomic ideal gases, which is the case because it's the simplest, the case we've mostly dealt with so far, here's the CV, and here's the CP for monatomic ideal gases. So you can see that these relationships that we've used in the past are special cases of these relationships up here, which hold for any substance, at least approximately. All right, that brings us to the most important equation of state for the rest of the class going forward. We haven't talked much about chemical potential, but now from this point on, we will start talking a lot about chemical potential. You can tell from the name, chemical potential, that this quantity ought to be important for chemistry, and it is. We've seen also that chemical potential can be related to the molar Gibbs free energy. We know that Gibbs free energy is important for chemistry. So for both reasons, we can see that this is going to be an important quantity later on. We also saw earlier that the chemical potential is the driving force for movement of chemicals or movement of chemical species from one point in space to another. It's also the driving force for movement of chemical species from products to reactants. So it's the driving force for chemical reactions. And of course, chemistry is all about chemical reactions, so of course, the chemical potential is really important. Here's the equation of state. The chemical potential for a particular substance I, so for water or for methane or for protein, for any chemical species I, there's a standard state chemical potential, and we'll talk much more about this in sections yet to come, plus a term that accounts, it turns out, for translational entropy changes that take place, say, during a chemical reaction or any other kind of chemical change. And that term is R times T times the natural logarithm of a quantity that's called the activity. That activity is basically an effective concentration, and we'll see what that means down here below. We'll go through what the best choice for activity is for a whole variety of different situations. But let me emphasize right at the beginning that putting the activity in like this, putting this sort of vague quantity called activity in there, is a way of making this expression valid for a whole bunch of situations where maybe it wouldn't otherwise be valid. Basically, we're free to fool around with the definition of this activity in order to make this overall expression at least approximately valid. And what that means from our point of view, from a practical point of view, is that this expression is approximately valid for the right choice of activity for a very wide range of cases. There are very few cases where this expression really can't be used at all. There are a few such, but they are quite rare. All right, so that's our expression, and we will use it over and over again when in the coming sections. Let's look. We'll talk about this standard state term later. That actually is important. It's related to the standard state Gibbs free energies, molar Gibbs free energies that you look up in tables, but we'll see what that relationship is later. Let's focus on the activity for now. So here's an example of using this equation of state for a salt solution in water. We can write down the chemical potential for every species that's present in our system. There's one chemical potential for every species. There's not just one chemical potential for the whole system. There's one for every chemical species. So for the solvent, for water, the chemical potential for the water is the standard state chemical potential plus RT logarithm of the activity for water. And because water is the solvent, the best choice for activity is to use the mole fraction of water. For a dilute solution, the mole fraction of the solvent is almost always very close to 1. It's 0.99 or 0.999 or something like that. And so the activity for solvents is almost always very close to 1. When you take the logarithm of 1, that means this whole term just disappears. That isn't invariably the rule, and for very accurate work, the fact that this isn't quite 1, it's a little different from 1, should be taken into account. But most of the time for solvents, the activity is the mole fraction, which is always close to 1. Now for the solutes, the sodium ions, the chloride ions that are present in a salt solution, there's also a chemical potential. There's a standard state chemical potential plus an activity for the sodium. And that activity is usually taken to be the molar concentration of the sodium. And that's the same thing as the molar concentration of the NaCl itself, of course. And likewise for the chloride ions, there's a molar concentration of chloride ions, which is the same thing as the molar concentration of the sodium chloride, thought of as a species in its own right. All right, we'll see lots of examples of how these are used as we go along. All right, so that's the equation of state. Let's talk about the general rules for the activities. For gases, the best choice for activities usually is to use the pressure divided by a standard state pressure. I put these things called activity coefficients into all of these expressions, but usually you can ignore them. The activity coefficients are almost always 1. If the activity coefficients matter and they're not close to 1, then I will key you in or warn you whenever that happens, because it happens rarely enough that usually I'm just going to assume them to be 1. In which case you can ignore this whole front part here. The activity is then basically just the partial pressure divided by the standard state partial pressure, and usually the standard state partial pressure is 1 atmosphere, or sometimes 1 bar, which is almost the same thing as 1 atmosphere. And what that means is the activity is oftentimes taken to be just the partial pressure in atmospheres, right? If the standard state partial pressure is 1 atmosphere, then in atmosphere units, this is just a 1 underneath, and the activity becomes effectively the same thing as just the partial pressure in atmosphere itself. For a different situation, if the chemical species in question is the solvent, like the water case up above here, where the water was the solvent, then again, ignoring this activity coefficient, the best choice, or usually the most useful choice, is to choose the activity approximately equal to the mole fraction for the solvent. And that's true whether it's water or some other solvent. If your solvent is, let's say, hexane or an ether or something like that, one of the common organic solvents, still you use the mole fraction. And the reason you use the mole fraction is because the activity of the solvent itself doesn't vary very much, and the mole fraction reflects that truth. Finally, the most common case, this is the case that's 90% of the time used. The activity for a dilute, non-ideal solute is usually, again, ignoring the activity coefficient here, just a concentration divided by a standard state concentration. The standard state concentration is usually 1 molar, which means that the activity is essentially the same thing as the molar concentration of whatever chemical species we're talking about. The other choice that's common in some places, though much less common in the actual scientific literature than it is in textbooks, textbooks like molality for some reason, is molal concentration. So molar concentration, of course, is moles per liter. Molal concentration is moles per kilogram of solvent. For water, a kilogram of solvent is almost the same thing as 1 liter, so molar concentration and molal concentration are almost the same thing. But molar concentration is actually theoretically much better justified. Molal concentration is popular with analytical chemists because you can weigh out the mass of the solvent much more accurately than you can usually measure the volume of the solvent. And so analytical chemists like that accuracy, and that makes molal concentration popular in some textbooks and in some settings. But in the literature that I've seen, at least in my experience, molar concentration is much more common, and from a theoretical, statistical, mechanical point of view, molar concentration is also best justified. All right, that is the set of standard equations of state that we'll use in developing our thermodynamic applications for the rest of the class.